Good afternoon, everyone. We're from Group 6, and today we are going to present our systems modeling final project. Here are our group members. Bangladesh is one of the most disaster-prone countries in the world due to its geographic location, topography, and high population density. It frequently experiences natural disasters such as earthquakes, floods, and especially tropical cyclones, which severely affect southern regions. In this project, our goal is to design, simulate, and compare various logistic strategies for delivering 80,000 tons of disaster relief goods to the affected people in the regions of southern Bangladesh within a 40-day period, serving approximately 2 million people. However, there are several general constraints we must consider in the planning and simulation process. These include damaged infrastructure, limited accessibility to remote or flooded areas, budget constraints, and overall logistical limitations due to the scale of the operation. The map highlights the cyclone-affected areas and underscores the urgent need for an effective and adaptive logistics plan. Next. Now let's talk about the demand, supply sources, and key constraints. After the cyclone, around 2 million people in southern Bangladesh require urgent humanitarian. Around 2 million people in southern Bangladesh need shelter, food, medicine, and fuel. The total demand is 80,000 tons over 40 days, equivalent to 2,000 tons per day or 1 kilogram per person per day. In this first 5 days, 10,000 tons will be distributed from government stockpiles in Dhaka, Chittagong, Mulna, and Pabna. From day 6 onward, 70,000 tons will arrive internationally, mainly from Singapore via Dhaka Airport and Chittagong Port. There are major infrastructure and transport constraints. Roads are impassable for the first 2 days. Some bridges cause delays, and port access is limited to Dhaka and Chittagong. Early transport relies on helicopters, which are costly and limited in capacity. Small trucks can operate from day 3 and larger ones from day 15. Planes and ships offer longer range but with high cost and delay. The key point is that relief efforts must adapt to shifting access and transport options as infrastructure gradually recovers. Next.
Here is our model simulation. And moving on to the model conceptualization. So for the model concept, we use transport modes and availability such as air helicopter for day 1 onward and ground 3-ton trucks day 3 until 14 only, and ground 6-ton trucks day 15 onward, and international such as ship or plane day 6 onward. And for the modeling approach, we use linear programming to optimize the logistic plan, focusing on minimizing costs while maximizing delivery effectiveness. LP accounts for daily demand, cost of each mode, availability over time, and impassable infrastructure. And for the model construction, the key properties such as the source, there are vehicle Boeing, vehicle ship, vehicle heli, vehicle small truck, vehicle big truck, and goods Singapore, goods Dhaka, goods Chittagong, goods Khulna, and goods Papna. So source is divided into 2 types, vehicle types and goods from different location. And for the server consists of loading and unloading of goods from 2 different location. And for the sink, receive the end products after different paths. And for the combiner, so the combiner function to combine the path from different nodes, and the separator, so separator 1 and 2 function to separate the goods going to sink or continue. And for the separator 1 is the Boeing, and the separator 2 is the ship, and for the separator 3 is to decide the thing to camp or vehicle. And here is our model construction.
And to verify our model, first we check the flow works, which is we check the entities moving smoothly from the source through the server until the sink. Second is the connection is valid, meaning that all blocks are properly linked with no breaks. Third is the routing logic, meaning decisions and branches are connected correctly. Fourth is no stuck items, meaning no loops or dead ends. Fifth is resources or queues present, meaning buffers and processes are working. And finally, the final output, meaning that we check the items exit correctly at the sink. And to validate, we validate the delivery achievement. We successfully transported 78,282 tons of the targeted 80,000 tons, reaching over 97% fulfillment. And the deadline adherence, meaning that all deliveries were executed within the planned 40-day period. And the cost performance, meaning the total cost of logistic was $25 million, demonstrating cost effectiveness compared to the total value of goods. So the overall assessment is our model produces credible and practical outcomes and satisfies the logistical requirements outlined in the disaster response scenario. So from all of this, we can take away that the model is both valid and reliable for evaluating relief distribution strategies effectively, balancing costs and timelines while supporting scenario experimentation for decision making under uncertainty. Next.
Okay, for the model usage, we implement 5 workflow. The first one is visualize the entire workflow and material flow. Then we identify bottlenecks in the process. Next, improve decision making through data-driven simulation. Then we optimize resource usage such as machines and transporters. And then finally, estimate performance metrics like throughput, delays, and cycle times. We collect the data, average wait times in queues, machine utilization, total output, item processing time, cycle time, and number of items reworked or scrapped, if applicable. Next.
So in conclusion, here's a summary of our key findings and the best logistics schedule from our semi model. First one is we built a logistic model that identifies cost-effective strategies while staying within budget. And then the model proves that delivering 80,000 tons of relief in 40 days is possible even with damaged infrastructure. And then it offers a reliable foundation for real-world disaster planning. So for the best schedule, day one, a helicopter from local survival for inaccessible areas. And then day 3 and 5, small trucks begin operating where roads are partially open. Day 6 and 11, emergency air shipment distributed by small trucks. Day 11 to 39, boats bring bulk goods distributed by small plus big trucks. And then day 40, final top-up by plane. And for the impact, we use boats for inbound shipping and big trucks for efficient regional delivery. Overall, this plan balances speed and cost, making it ideal for large-scale disaster response. So this is our appendix. Okay. That's all from us. Thank you for listening to our presentation.